Welcome to clickmyproject.com. Let's discuss about the product. Our product is a 16 KB spin transfer torque random access memory with self-enabled switching and pre-charge sensing schemes. Spin transfer torque magnetic random accessory memories, that is STT-MRAM, is considered one of the most promising non-volatile memory candidates thanks to its excellent performance in terms of access speed, endurance and compatibility to CMOS. However, high power supply voltage is required in the conventional STT-MRAM writing circuit, which results in high power consumption. In addition, it suffers from stochastic switching behavior and process voltage temperature variations. These make power efficient and reliable read-write circuits become critical challenges. In this paper, we present novel circuits and architectures to build a 16 KB STT-MRAM design with low power and highly reliability. For example, the self-enabled switching schemes reduces the power consumption effectively, and the 4-placed sense amplifier improves the robustness to process variations. Using an accurate compact model of 65 nm STT-MRAM and a commercial CMOS design kit, mixed transient and statistic simulations have been performed to validate this design. Flip-flops and latches are used as data storage elements. Such data storage elements can be used for storage of state. That means we can storage of information in the name of bits. Flip-flops can be either simple, that is transparent, or opaque, or clocked, that is synchronous or edge-triggered. Here we propose a design of low-power magnetic flip-flop using CMOS technology. The proposed flip-flop design is based on CMOS dyno latch technology. That means we have included the dyno latch methodology in this paper. So this is considered as our proposed system. That means the enhanced method. Recently, magnetic random accessory memory, that is MRAM, is considered on the most promising candidates to build up universal memory. It has many advantages such as non-volatile, fast read-write speed, unlimited endurance and compatibility to CMOS. Storage elements consist of one magnetic tunnel junction, that is MTJ, monofiller, and one word selection transient driven by one word line. An MTJ acts as a resistor with low or high value depending on the relative magnetization of the two material layers, either parallel and anti-parallel. This low or high resistance allows it to be used as non-volatile binary state. The tunneling magno-resistance, that is TMR, characteristics the amplitude of this resistance changes, while the transient resistance area, that is RF, product based on RP characteristics the resistivity of the tunnel barrier. In practical samples used for MRAM, MGO is used for the tunnel barrier and the TMR rise up to 200% for RA between 5 and 30 ohms micrometer square. The conventional switching MRAM switching approach, which is based on inductive magnetic field writing with current greater than 10 mA, is the first generation of MRAM, which faces several limitations. That is, MJT needs a higher current, that means greater than 10 mA, to reverse the magnetization of free layer with scaling down the size. This causes many problems such as increasing power dissipation, low storage density, low reliability and so on. This STT MRAM builds of the second generation of MRAM. Using STT mechanism, a low bidirectional current passing through the MJT can switch its configurations. Here, I write is larger than the switching threshold current. The reading operand of STT MRAM is to pass low current to detect the resistance difference between RAP and RP. read current flow through the MGT can switch the MGT state by thermal activation, which can be described by the Neil-Brown model. This is critical issue in the use of in-plane magnetic anti-circuitry with low thermal activity energy using the peripheral magnetic anisotropy with high E. This reads disturbance. This is the system flow design of our design. So initially we are starting the design using CMOS technology, and our design goal is to design a STT-MRAM. So that is based on magnetic flip-flop. Okay, so we have to start with the design of magnetic flip-flop, and then as our enhancement, as we already discussed, our enhancement is dyno latch design. So with technology, with the enhanced technology of dyno latch design, we are including that CMOS design with magnetic flip-flop. That means in the existing method STT-MRAM, we are including CMOS dyno latch design with the same CMOS design methodology. So finally we are applying all the designs into STT-MRAM. So by the result of this design, we are obtaining, that is our goal. Finally we are getting low power consumption. That means ultra low power consumption from the design of STT-MRAM. So during actually our goal is to reduce the power consumption during the write up time. So that's what we have mentioned here. While writing operation is performed, ultra low power consumption is performed. So for this design we are conducting on Tanner EDA.
This is the tool we are using for the simulation. This tool is called the Tanner tool. In Tanner tool, basically it has lot of sub devices. That means we are having SED, WED, LED. Like this, we are having separated layout designs for waveform designs and for circuit designs. So similarly, we are having separate lines for designing of separate parameters. So our CMOS design is performed in SED. So our performed design produces the output in WED. The T-space, that means we can export the code of the designed circuit in T-space. So we can open the code in T-space and we can modify it as our requirement. So we are using, we are using SED for the circuit design, T-edit for the extra modifications, and WEdit for the output design and analysis of the output waveforms. So this is the tool we are using for us here. By clicking this, we can start a new project. So to start every new project, we have to open a new cell. So by clicking the cell, we can design a new circuit design. So in the cell, we can include lot of libraries which consist of a transistor, CMOS transistor, resistors, capacitance, such as general devices. So after we designing, we have to set the setup simulation. After that, we have to save the file and we have to execute it. So if we executed the circuit in correct manner, we can get the output in WEdit.